presentation by Marius van der Wijden about go-ethereum. Thank you, Marius. Give him a warm welcome.
Yeah, thank you for having me. My name is Marius. I work at the Ethereum Foundation for 3.5 years now, on go-ethereum mainly. And so this presentation, it's going to be quite weird, but I hope you bear with me and you enjoy the format. So I kind of up a bit because this presentation is meant to be more like a workshop, but I'm just going to try to do it anyway. So how did this presentation came about? I gave a talk last year at ETH Amsterdam where I went through the go-ethereum codebase and showed how the transaction flows through different modules in go-ethereum, what we do there. And we started with submitting a transaction, then we created a block out of it, and in the end we ended on EVM execution. Today I want to trace another transaction, but now we don't start at the ETH API, which is the entry point where you send your transactions if you send them via JSON RPC. But today we want to start at the engine API. So this is roughly how your node, if you run an Ethereum node, looks like. Post-merge you have two nodes. You have the consensus layer node and you have the execution layer node. And the consensus layer node basically tells the execution layer node what to do. So there's a lot of new people coming in, which is quite funny. This kind of glue between those two nodes is called the engine API. And this is where we're going to start our journey today. And yeah, and I only know where to start. I don't know where we end up. So let's see. Let's just go with it. So the engine API, as I said, is the glue between the consensus and the execution layer. For those who don't know, probably not that many of you, Geth is an execution layer node. So it's responsible for executing the transactions. And this engine API has a few functions that are standardized. And the first function that we standardized was new payload. The consensus layer uses this function to tell the execution layer about a new block. And we have to execute the block and say, yes, it's a good block, no, it's not a good block. But we don't update our current head. So we don't set the fork choice. That method is called fork choice updated. With this, the consensus layer tells the execution layer, okay, this block that I just gave you, this is the new head. Why is this split in two methods? Because there could be the case where like 5 different blocks arrive at the consensus layer node at the same time. We need to make sure that all of those blocks are correct. And then the consensus layer will aggregate attestations and choose which of those different blocks that are currently competing for the head is the best one right now. And this is what the consensus layer node tells us in fork choice updated. Fork choice updated has also another small functionality. Optionally, the consensus layer asks us to build a block on top of the current head. So the consensus layer node tells us, okay, this is the head that you should have, and please build a new block on top of this, because we've been chosen to produce the new block. And so this is what happens in fork choice updated. And in get payload, we can retrieve this pending block. And then those are the big 4 methods that we need. And there are 3 additional methods that are just for convenience. Get payload bodies by hash and range. They return old blocks to the consensus layer. this was implemented because the consensus layer might not want to store all of the old blocks because the execution layer already stores all of the blocks, so we would need to store them twice. We don't want this, so we need this method. Exchange transition configuration makes sure that the execution layer and the consensus layer are both configured correctly, and exchange capabilities tells the consensus layer which of those functions are available. And because we have to further the network, we have to work on the network, we have to change the engine API. We have built in versioning into these functions, and with exchange capabilities, we can tell the consensus layer node, hey, I support these versions, and then the consensus layer can say, okay, this node doesn't support this version that I want, so I'm going to show the user an error or something. Okay, now to the fun part. We're going to look into the code and actually see where all of this is happening. The engine API is located in go-ethereum, is located in the ETH/catalyst package. It was called Catalyst before this was way before any work on the merge was being done. We started with this proof of concept called Catalyst, and it's kind of like we never really moved the engine API out of this package or renamed the package, so everything is still there. And what you can see here is when we do exchange capabilities, we send the consensus layer these methods. So these are the methods that we support. You can see fork trace update at v1 till v3, get payload v1, v2, v3, and so on. And now our journey starts with, new payload. Sorry, as I said, this is the first time I'm doing this. Okay, so with new payload, the consensus layer tells us this is a block that I received. Please make sure that it is well formed, executed, and store it. But don't update your state yet. And so we get this executable data, which is basically, so before these functions are called, the JSON that we get from the consensus layer is turned into these internal types. Well, we're not going to look at that, yeah. So that happens before this method is called, and so. The first thing we do is we turn this executable data into a block, and so this happens here, where we have some transactions that are just byte slices, and we have to turn them into transaction objects. And this is also where we do the first number of verifications on this data. So, for example, after the merge, the extra data field in the block header has to be less than 32 bytes, and so we check this here, for example. And then we unmarshal stuff, and for here we compute the transaction root. So the header of the block header contains the root of the transaction tree, which means we take the transactions, we build a Merkle tree of them, and this root of this Merkle tree is put into the header. And we need to make sure that the transaction that we have matches to this root, and that this is what we do here. Oh, actually, this is for the withdrawals. We do the same thing for the transactions here, and then we construct our header. And with this header, we add the transactions to it, and then we compute the hash. and we verify that the block hash is correct. This is just a basic verification that we have to do whenever we get a block. We have to verify, okay, if we take this data that we just got from the consensus layer and we create a block out of it, is this a valid block? Does it compute to the correct block hash? And so what we do in the engine API now is we look in our local blockchain, okay, did we see this block already? If we saw this block already and it was verified, we can just say, okay, yeah, we saw this, we verified it in the past, we will just return okay. If we haven't seen it, then we need to check whether this is a known bad block. Have we seen this block and verified it to be bad before? So was there something wrong with it? And this is what we do in check invalid ancestor. It checks whether this block was ever marked invalid, or if the parent of this block was marked invalid, or any ancestors of this block were marked invalid. So, for example, if I get a block and it is built upon another block that is invalid, then this new block is also invalid, of course. And so after we check this, we retrieve the parent block. The parent block is just the block that has the parent hash and the number, in our number, -1. So it's one previous. And then there's some stuff about the block time. So every block has to be consecutive. That means our block time has to be bigger than our parent block. And also some checks about the total terminal difficulty that was needed for when we actually merged. And so I think this is very Geth specific, but we don't start synchronizing on new payload. So if someone gives us a block and we don't know anything about this block, we don't know what the parent is, we need to ask the network for the parent. Because it might be that we were offline for a bit, so we didn't see the parent arriving at us, so we have to start a new sync cycle. But we kind of view this new payload method as kind of untrusted. It's called with payloads that might or might not be wrong. There might be payloads that are in the same slot, but one of them is the correct one is the incorrect one. They build on different blocks. And so if we trigger the sync here, so the synchronization is a very complex and inefficient process. We need to ask the network for the parent, then the network tells us the parent. And then maybe this parent is, the parent of this block is something that we have already. Then we can say, okay, it's fine, I'll just execute the parent, and then I execute the new block, and then I'm at the head and everything is fine. But what if the parent of the parent is not there? And so I have to ask the network again, what's the parent of the parent, and so on. So triggering a sync is a very complex method, and we only do this on fork choice updated. The problem is, on fork choice updated, we don't have enough data to trigger the sync. Well, in theory we have, in practice it's kind of murky, but what we do is when we get a new payload where we don't know the parent, we will just put this in storage, and if the consensus layer says you need to put this block as your head by calling the fork choice updated method, then we will go to the network and start the syncing. So this is what we do here. We delay the payload import. Basically, we just take this payload, put it in our storage, wait for the next fork choice updated. If the next fork choice updated references this block, then we start the sync. And then, so in order to execute all of the transactions correctly, we need to have the state for them, right? We need to have the, if I want to verify that a certain transaction spends the money correctly, I need to know what was the balance of this account before the transaction. And so this is what we do here. We check, do we have the state for this parent block? And if we have the state for the, if we don't have the state for the parent block, we cannot do anything. So we have to just warn and accept the payload, but we cannot say whether this payload was valid or invalid because we don't have the state to execute it. And now comes the really interesting part. We actually execute the block. This is what we do in insert block without sethead. And this method kind of only calls insert chain. Insert chain gets a number of blocks and whether we want to set head. Set head means this is the new canonical block and I'm going to set my current header to this. And we don't do this in new payload, but only in fork choice updated. So this insert chain is kind of a long method. It's not really important. What we do before we execute the block, we have to verify the header that it was that everything was correctly built. I think we can go there. So we have the kind of the rules around the block are all written in the consensus package, and here we have the different algorithms that we support. So the beacon is for post merge, click is for pre-merge, click is for like test networks, and ETH is for pre-merge. And so what we do here, verify header. We just check is the terminal total difficulty reached, and if it's not reached, then we use, then we are pre-merge, and we have to use ETH to verify that the header was built correctly, and otherwise we use the post-merge method. And here we have, again, some of the checks are duplicated here. That is because this part is used from all over the place. Like the consensus, these consensus rules are the actual consensus rules. The other verification that we have is more like a, did we unmarshal this block correctly or did something break there? This is where the actual consensus rules are verified. And this is also verified during the sync. It is not only like verified during block execution. So this is also, whenever we get a block, we have to verify it with this. And so if we go back, yes, here we verify the headers, and then we go through the blocks. We see if there's some reorgs. It's not really interesting, but the actual execution happens. Where's the actual execution? Sorry. Here. This is where we actually execute the block. Basically, as I said, in order to execute the block, we need the state of the previous block, all the balances, all the smart contracts, everything that is written in the smart contracts. We need this, and this is what we do here. StateDB is kind of an abstraction that we do on top of the state, where we can write to it, but it doesn't have to be flushed to disk. So this is basically we execute everything in memory, and then we can call some function, and then the root of the Merkle-Patricia trie is computed. But we don't have to do this on everything, like on every insert. And so this is where the actual block processing takes place in the block processor. And this is just the interface. So this method lives in core/state processor. This is where a lot of these very internal execution happens. And so what we do here, before we can execute the block, we have to apply the DAO hard fork to our state. If we are on the block that enabled the DAO hard fork. Otherwise, we create a new EVM environment and set the transaction context, and then we call this apply transaction. And in apply transaction, we do apply message. And this is where the actual EVM execution happens. So this is kind of where we also ended up in the last talk. I'm pretty sure none of you have ever listened to the first talk, but it's fine. This is where the actual EVM execution happens. And before we can do any execution, we have to verify that the sender of the transaction has enough money to cover the transaction cost. And this is what we do in pre-check, where we verify that the nonce is correctly of this transaction, and we verify that the sender is an EOA, so you cannot send money from accounts. It's just, yeah. We hope there will never be like a hash collision between an EOA and an account, but now it's written in protocol. And then we have to verify that the base fee is correctly, and we have to also now with 4844. So as you can see here, it says blob hashes. That means there's also the logic for 4844 already implemented, already in master. But yeah, so in addition to the normal fees, we also have to compute the blob fees and make sure that the person, the sender, has enough money to cover everything. And so this is where we actually compute how much it would cost. And here is where we verify that the sender has enough money. So we get the balance from the sender, and we verify if they have enough money in their account. And also we verify if we have enough gas in the block left, because the block can only be 30 million gas. And so we need to make sure that if we charge this transaction, we are not going to go over these 30 million. So this is what we also do here. And then, so this was the pre-check, and now we compute the intrinsic gas, and then we prepare the state. So we create the access list. We make sure to put all the precompiles into this list. So when someone calls a precompile, it's cheaper than if they call like a normal address. And then we have either a transaction that creates a contract, or we have a transaction that calls something. And so if we have a contract creation, we call the create opcode. And if we have a normal call, we just call the call opcode. And this is where we have the call. yeah, so I think this is kind of where I'm going to stop, because this is also covered by this other talk. But basically, all of the functionality, what happens within the EVM is in core/VM. This also has the opcodes. For example, this is the static call opcode here, or we have the create2 opcode. And yeah, so if you ever find yourself in a spot where you want to add an opcode, you need to do it here. Yeah, that's basically my talk. I still have some slides. This is what I'm going to talk about in another deep dive into go-ethereum. So there's hopefully going to be a third one of these, where we talk about some of the other things. Thank you very much for listening.
We have room for a few questions if someone has a question for Marius. In the back. Yeah, two.
Hello, thank you for your presentation. I was wondering, from the prospect of layer 2s, sometimes execution layer actually needs information from consensus layer. Is it actually possible for the execution layer to get information from the consensus layer? An example of this would be, what is the last epoch or block that has been finalized?
Yeah, so this is the last finalized one. That is no, there's no way for the execution layer to contact the consensus layer. The data flows in one direction. The execution layer tells the consensus layer what to do. The consensus layer tells the execution layer what to do, and checks for what they said. What you just talked about, the finalized hash in forktrace updated. We get this update from the consensus layer, and this sets the head block hash, the saved block hash, and the finalized block hash. So you can kind of emulate this two-way street in that you just like provide all the data from the one side that the other side needs.
But this is not available for use by, for example, smart contracts, right?
Yes, it is. So we take this and we mark the blocks that are finalized. And so if you go into your, if you have a dApp and you say I want you can say you want the latest block, right? Get block by number latest, or get block by hash latest or something. And you can do the same thing with finalized. You just say get block by hash and then finalized, and you will get the final block. This is, I think most of the clients already support this, yes.
So Geth is in development for like 8 or 7 years now?
Could be.
What's the hardest part of maintaining it these days?
The biggest challenge is the state, because it's so big. I think it's around 70 gigabytes. So this, the state is all of the accounts, all of the balances, basically the state trie. And right now we maintain 2 copies of it. We maintain one copy for basically only for reading. This is called the snapshot. And we maintain one copy that is for computing the state root, and that is the state trie. And one thing that we've been working on for 3 years now is how to store the state trie. And previously we stored every trie node by hash, and now we just merged the path-based storage. And this will get rid of this problem where you start your node and you sync, and you have like an 750 gigabyte node or something, and then you let it run for a while and it exponentially grows. And then you can shut it down, you can run the prune procedure, delete a bunch of stuff, and then it's 750 gigabytes again. So the problem there is previously we stored data. We stored some data that we didn't need to store, but we didn't know that this data is, whether we can get rid of this data. Now with the path-based storage scheme, we know exactly which data we can delete, and this will also greatly reduce the size of our archive node. There are some preliminary numbers, but it's an order of magnitude less than what we need for storage right now, and it won't grow as quickly as with a hash-based storage. So yes, storing the state is our biggest issue because it changes so much, and we have to recompute the trie every time.
Okay, thank you. Let's give an applause, people, for Marius. Thank you.